Probability amplitudes. Now we discuss about probability amplitude. Probability amplitudes. Evidence was presented in the preceding discussions that under certain circumstances, physical systems of quite disparate nature, but usually on the atomic scale, have the common properties of randomness and interference effects that have no classical explanation. These general properties are the indicators or the signature of the existence of basic physical laws that are not part of our normal everyday view of the way the world behaves, which immediately poses the problem of determining and clearly stating what these fundamental laws are. But there is in fact second problem that has to be dealt with here. In order to state these basic laws, the question arises as to whether or not the concepts and mathematical language of classical physics is adequate for the task. We have seen that the mathematics of wave works fine for particles moving through space. From the wave functions, which can be derived by solving the Schrödinger wave equation, information on the position and momentum, angular momentum, energy, and much else besides can be obtained. But we have also seen that the wave function cannot be used to describe spin. Apart from anything else, spin is a discrete variable with a finite number of values, unlike the position of a particle, which can vary in a continuous way. So what is needed is a mathematical language in terms of which these laws can be expressed, but which can assume outwardly different forms when applied to different physical systems. The two problems are not independent. The process of determining what the physical laws are guides us in the development of mathematical language needed to express these laws. The outcomes of all this in and other examples of what has been termed the unreasonable effectiveness of mathematics in physics is a mathematical language that was already well known to mathematicians in the early days of the quantum theory. The mathematics of linear vector spaces. It was a British theoretical physicist, Paul Dirac, who played a major role in formulating quantum mechanics in this way. He was inspired to do so, in part because of the above-mentioned need for a theory that could cope with both particle spin and particle motion through space. What this work does, amongst other things, is bring into sharp focus the problem of defining what is meant by the state of quantum system and how a quantum state is to be represented mathematically. A further consequence of his work is a succinct notion which encapsulates both the physics and the mathematics. The direct bracket notation, which is used amongst other things to represent the state of a quantum system. The first issue to be dealt with here is that of coming to terms with what we mean by the state of a system, following which we look again at the two-slit experiment, which sets the sense for the development of the Dirac versions of quantum mechanics.